Math 1143, Test 3 Review Sheet, Chapter 3 Material, Section 3.6. Solve each equation for the specified variable. For this one, capital S equals 62 plus 317 times e to the negative kt. Solve for k. So first we'll subtract 62 from both sides. S minus 62 equals 317 times e to the negative kt. Then divide both sides by 317, and we get S minus 62 over 317 equals e to the negative kt. We want to solve for k, so k is an exponent, so we can take the natural log of both sides. The natural log of S minus 62 over 317 equals the natural log of e to the negative kt, but the natural log of e to the negative kt simplifies to negative kt. We want to solve for k, so we'll just divide both sides by negative t, and we get k equals the natural log of s minus 62 over 317 divided by negative t. In the next equation, capital T equals 84 minus 14 times the natural log of lowercase t plus 3. Solve this equation for lowercase t. So we want to isolate the natural log of t plus 3. So we'll subtract 84 from both sides. We get capital T minus 84 equals negative 14 times the natural log of t plus 3. Then divide both sides by negative 14. Capital T minus 84 divided by negative 14 equals the natural log of lowercase t plus 3. And then we can convert this logarithmic equation into an exponential equation. The base of the logarithm is e, so if we raise e to the exponent capital T minus 84 over negative 14, that's equal to lowercase t plus 3. And then to solve for lowercase t plus 3, we just subtract 3 from both sides, and we get lowercase t equals e to the capital T minus 84 over negative 14, and then minus 3. In the next equation, the pH is equal to the negative base 10 logarithm of the hydrogen ion, and solve for the hydrogen ion. So the first thing we can do is multiply both sides by negative 1, so we get the negative of the pH equals the base 10 logarithm of the hydrogen ion, and then we can convert this logarithmic equation into its exponential equation equivalent. The base 10 raised to the negative pH is equal to the argument of the logarithm, which is just the hydrogen ion. So that's the complete problem there. The next problem is a word problem. So on this one, we have the size of a population of sycophants started out at 512 at 10 a.m. and it was observed that the population was 1280 at 2 p.m. So if we assume exponential growth, we can find the growth constant. The model, the continuous exponential growth model is y equals y sub 0 times e to the kt, where y sub 0 is the initial population, and that's given to be 512. And we're told that when t is equal to 4 hours, from 10 a.m. to 2 p.m., that's 4 hours. When t equals 4, the population has grown to 1280. So we're going to replace y with 1280. The initial population is 512. And when t is 4, we have e to the 4k. And then we're just going to solve this equation for k to get the growth constant k. So first divide both sides by 512. And notice that 1280 divided by 512 is 5 halves, or 2.5, so 2.5 equals e to the 4k. Then take the natural log of both sides. The natural log of 2.5 equals the natural log of e to the 4k. but the natural log of e to the 4k is just 4k. So the k value is the natural log of 2.5 divided by 4. And then in part B, we'll write down the complete function, y equals the initial population, 512, times e to the natural log of 2.5 over 4 times t. This is the value of k. Determine the size of the population at 8 p.m. 8 p.m. is 10 hours after 10 a.m., so when t is 10, the population is 512 times e to the natural log of 2.5 divided by 4 times 10. And then you can use a calculator to come up with a number for that. In part C, find the doubling time. Since we have exponential growth, it's just a matter of time until the initial population doubles. And when it doubles, the population will be 1,024. So we replace y with 1,024, set it equal to 512 times e to the natural log of 2.5 over 4 times t. Then we solve this for t. That will be the doubling time. So first, divide both sides by 512. 1,024 divided by 512 is 2. So 2 is equal to e to the natural log of 2.5 over 4 times t. We want to solve for t. It's in the exponent, so we'll compute the natural log of both sides, the natural log of 2 on the left-hand side. And we know by now that the natural log of e raised to an exponent is just the exponent. So in this case, the natural log of 2 is equal to the natural log of 2.5 over 4 times t. And then the doubling time we can find if we just multiply both sides by the reciprocal of the natural log of 2.5 over 4. So the doubling time is 4 times the natural log of 2 divided by the natural log of 2.5. Then use a calculator to come up with a number. This is measured in hours. And if you want to find the time of day, just add this to 10 a.m. Okay, find the amount of time it will take until the population reaches 8,000. So this time, we still use the same function, but this time we replace y with 8,000, set it equal to 512 times e to the natural log of 2.5 over 4 times t, and then solve for t. So we'll divide both sides by 512 to start with, and note that when 8,000 is divided by 512, it simplifies to 125 over 8. So 125 over 8 equals e to the natural log of 2.5 over 4 times t. Then we take the natural log of both sides. We get the natural log of 125 over 8. And the natural log of e to the exponent is just the exponent. So we just have the exponent natural log of 2.5 over 4 times t. And then to solve for t, we can just multiply both sides by the reciprocal of the natural log of 2.5 over 4, and we get t equals 4 times the natural log of 125 over 8, all divided by the natural log of 2.5. And this is measured in hours again. Okay, the next problem will involve exponential decay. So this one, let's see, we suppose that 35 pounds of atomic bomb shrinks to 28 pounds in exactly 5 days. So if we assume exponential decay, we can find the decay constant. So the model still looks like y equals y sub 0 times e to the kt. The initial quantity this time is 35 pounds. And we're told that when t equals 5 days, when t equals 5, the y value, or the amount left, is 28 pounds. So we use this information to determine the decay constant k, replace y with 28. The initial quantity is 35 pounds. Set that, and so 28 equals 35 times e to the 5k because t is 5. Then we proceed to solve this equation for k. Divide both sides by 35. 28 divided by 35 simplifies to 4/5, which is 0.8. So 0.8 is equal to e to the 5k. Then take the natural log of both sides. The natural log of 0.8 equals the natural log of e to the 5k, but the natural log of e to the 5k is 5k. And so the decay constant is the natural log of 0.8 divided by 5. And this is a negative number. You should know that the natural log of a number between 0 and 1 is negative. So this is a negative number for the decay constant. And so now we'll write the function y equals the initial quantity 35 times e to the kt, but now we know that the k value is the natural log of 0.8 divided by 5 times t. And then for part b, the number of pounds left when t is 12 days, well, we just replace t with 12, and we get y equals 35 times e to the natural log of 0.8 divided by 5 times 12. Then use a calculator to come up with this. This will be measured in pounds. Okay, find the half-life. So since it's exponential decay, it's only a matter of time until the quantity reduces to 1/2 that it started with. 1/2 of 35 is 17.5, so we set 17.5 equal to the function 35 times e to the natural log of 0.8 divided by 5 times t. Solve this for t, that will be the half-life. When you divide both sides by 35, the left-hand side is 1/2 because 17.5 divided by 35 is 1/2, and that's equal to e to the natural log of 0.8 divided by 5 times t. Then we compute the natural log of both sides, the natural log of 1/2 on the left-hand side, and the natural log of the right-hand side. The natural log of e raised to an exponent is just the exponent, which is the natural log of 0.8 over 5 times t. And then to find the half-life, we just multiply both sides of this equation by the reciprocal of the natural log of 0.8 over 5. So the half-life is 5 times the natural log of 1/2 divided by the natural log of 0.8. And this is measured in days. Okay, find the amount of time it will take until the atomic bomb shrinks to 5 pounds. Okay, so we're still using the same function. But this time we're going to replace y with 5 and then solve for t. That will be the number of days it takes for for that quantity to reduce to 5 pounds. So we set 5 equal to 35 times e to the natural log of 0.8 divided by 5 times t. Divide both sides by 35. 5 divided by 35 is 1/7, so we get 1/7 equals e to the natural log of 0.8 divided by 5 times t. Then take the natural log of both sides. The natural log of 1/7 equals the natural log of e to the exponent, the natural log of 0.8 over 5 times t. So the natural log of e to an exponent is just the exponent, so we'll just write the natural log of 0.8 over 5 times t. Then t can be found if you multiply both sides of this equation by the reciprocal of the natural log of 0.8 over 5. So the t, the amount of time it takes for atomic bomb to shrink to 5 pounds, is t equals 5 times the natural log of 1/7 divided by the natural log of 0.8, and this is measured in days. So to get a number you can relate to, just key those numbers into a calculator and you'll have your answer.